Okay, in the last video we have talked about the current. Now we are going to talk about what we are calling current density. It is similar to the electric field. If we are talking about electric field can be represented by lines. And when the lines of the electric field are concentrated, the value of the electric field increases. So we were talking about the number of electric field lines per unit area. In a similar way, we are going to talk about current density is the current per unit area. Here we say that to take a localized view and study the flow of the charge through cross-section of conductor at a particular point, we can use what we are calling current density. If the current is abbreviated as I, we are going to abbreviate the current density to be J. So J, the current density, has the same direction as the velocity of moving charges. So now I am talking about velocity of moving charge, and velocity is actually a vector quantity. So even the charge is a scalar quantity, so if I multiply charge by velocity, so the resulting value would be vector. So electric current density is a vector quantity, not like the current. The current is a scalar quantity. So J has the same direction as the velocity of moving charge if they are positive, and the opposite direction if they are negative. It is similar to the current. We said that if the moving charge is negative, so the current would be in the opposite side. If the moving charge are positive, so the direction of the current would be in the same direction of the charges. Now, for each element of the cross section, the magnitude J of the surface current density is equal to the current per unit area through the element. So J is current per area. So it is expected that its units would be ampere per meter square. So the SI units for current density is ampere per square meter. Ampere per square meter. To find out the total current in a specific area, we can obtain it by integrating the current density dot the surface area. And here we have a dot product between the current density and the area. So this dot product would introduce scalar quantity I. If the current density J is in the same direction of the area A, so this dot product would be J multiplied by A directly. So in the case that the surface area, the normal to the surface area, at the same direction of J, so I would be the integration of J dA. And if J is constant across the area, so it can be simplified as J integration with respect to dA or J multiplied A. In other words, if I'm talking about J here, instead it would be I over A. So J would be I over A. The current density can be represented by what we are calling streamlines. To understand the streamlines, let us remember the electric field lines. We saw that we can represent an electric field with electric field lines. Similarly, the current density can be represented with a similar set of lines which we call them streamlines. So They are stream of electrons or stream of moving charges. The current makes a transition from wider conductor at the left to narrow conductor at the right. So, because the charge is conserved during the transition, amount of a charge and thus the amount of current cannot change. So, in this case, however, the current density doesn't change. Here we have number of lines per unit area. We have the same number of lines per smaller area. So the number of lines per unit area here is greater than the number of lines here. So the current density in a wide conductor would be smaller than the current density in a narrow conductor. However, the total current is the same in both conductors because the number of charged passes through the wide conductor are the same as the number of charged passes through the narrow conductor. That's what we are saying, because charge is conserved during transition, the amount of charge and the amount of current I cannot change. So I here is the same here. But the current density changes because the value of the current over this area is less than the value of current of this area. It is greater in the narrow conductor. The spacing of the streamline suggests that increase in the current density. So if we reduce the spacing between the streamline, it means that the current density here is greater than the current density here. So for example, if this spacing between one line and the other is 1 millimeter here, the spacing here is 2 millimeters here. So it means that the stream current or the current density here is greater than the current density here. That's what we're saying. The spacing of the streamline suggests the increase on the current density. Seems that streamlines that are closer together imply greater current density. Now what actually happens inside the conductor? Inside the conductor, there are free electrons that can move from one atom to the other. However, this motion is in random motion such that the net motion or the net velocity of the electron in any direction would equal 0. So when conductor doesn't have current through it, its conduction electrons move randomly with no net motion in any direction. What happens when electric field is applied to the conductor? If an electric field is applied to a conductor, this electric field actually comes from a set of positive charge in this side and a set of negative charge in this side. So the electrons will try to move towards the positive charge. So in this case, the electron still moves in random motion, but with a net velocity or a net motion in the direction toward the positive charge which introduces the electric field. Or in other words, it would move with a net velocity opposite to the direction of the electric field. So when the conductor does have a current through it, these electrons actually still move randomly, but now they tend to drift with drift speed Vd in the direction opposite to that of the applied electric field that causes the current. This drift speed is tiny compared with the speed of the random motion. For example, in copper, the conductor are moving with a drift speed of order 10 to the power minus 5 to 10 to the power minus 4 meter per second. Whereas the random motion of speed is of order 10 to the power 6 meter per second. So it means that the order of the relative velocity is less than the order of random motion by 10 to the power 10. What about the drift speed and current density? Here we have cylindrical conductor representing a wire, for example, and we'll assume that we have moving positive charge and we apply electric field on this conductor. So this positive electric charge will move with derivative velocity in the same direction of the electric. If you are talking about negative charges, it will be moving in the negative direction to the electric. The current density will be in the same direction of the electric field, in the same direction of the motion of the electric charges, of positive electric charges. So current is said to be due to positive charges that are propelled by the electric field. The drift speed Vd of the conduction electron in the current through wire is related to the magnitude of the current density G of the current on the wire. For convenience, the equivalent drift of positive charge carries in the direction of the applied electric field. So if we assume that we are talking about positive charge, they will be going in the same direction of the electric field. But actually, the conductivity in metals are mainly due to free electrons with negative charge. Let us assume that these charges carriers all move with the same drift speed. So assume that all of them has a net drift speed Vd, and that current density G is uniform across the wire. So assume that the current density G is uniform across the wire. So it means that the total current I is J multiplied by A. So J is uniform across the wire cross section L. Now, the number of charge carried in the length L of the wire is N multiplied by the volume of the wire, the area multiplied by the length, where N is the number of carriers per unit volume, and A the area of the wire, and L is the length of the wire. So N multiplied by the volume would be the net number of charge carriers. The total charge carriers in the length L, each with charge has a charge electron E. So this is the number of the charge carriers and this is the value of each carrier. So the total value of the charge Q equal the number of charges multiplied by the value of each charge. So is N multiplied by A multiplied by L. N number of carriers per volume. A multiplied by L is the volume. E is the charge per each carrier. So the total charge is NALE. Because the carriers all move along the wire with speed Vd, the total charge moves through any cross section of the wire in a time interval L over Vt, because the length of the conductor is L and the velocity of the charge is Vd. So the time to pass from the first point at the conductor to the end point to the conductor is the length of the conductor over the derivative velocity Vt. So the time required is L over Vt. Now, if we remember, the current is Q over T. So the total current I would be Q over T, and we have proved that Q is the number of carriers per volume multiplied by the volume multiplied by the charge with each carrier. So N multiplied by A multiplied by L multiplied by E over T. T is L, the length of the wire, over the derivative velocity Vd. So by simplifying this, we can remove L with L, and Vd will be in the denominator. So it is N multiplied by the area multiplied by the electron of the charge per carrier multiplied by the derivative velocity. This is the current I. If I'm talking about the current density, it would be I over area. So the current density J would be I over area. It would be N number of carriers per unit volume multiplied by the charge for each carrier multiplied by the derivative velocity. N multiplied by E multiplied by the derivative velocity. If we want to find out the derivative velocity, we can say that the derivative velocity would be I over NAE, or in other words, it would be J over NE. The product N multiplied by E, N is the number of carriers per unit volume, so it is 1 over meter cube, and E is the charge of one carrier, so it is coulomb. So this is coulomb per meter cube. So the product NE with SI unit is coulomb per cubic meter, would be C over meter cube. Is the carrier charge density. For positive carriers, NE is positive. Thus, the current density J and VD has the same direction. If N is positive, so the vector J has the same direction of the vector of the derivative velocity. If we are talking about negative carriers, like electrons, so NE would be negative. So the relation between the current density J and the derivative velocity, J would be proportional to negative of the derivative velocity. So in this case, J and VD has opposite direction, or in other words, the direction of the current density would be opposite to the direction of the motion of the carrier.